Hello friends, welcome back to my YouTube channel Infinite Knowledge, and today we're gonna talk about one of the unique final year project, and that is a harmonic filter design. In this project we will consider MATLAB simulation, mathematical models, what is the actual requirement of the harmonic filter and how you can design a different harmonic filter. We will understand all the types of harmonics, passive harmonics filter in this video. So let's get started without wasting any time. You can consider it is a final year project as well as any MATLAB project, as well as for your understanding purpose also. So let's start with the introduction. We are not going with the problem definition. We will cover it after a harmonics understanding. So what is harmonic? Harmonics are a non-fundamental component that are present with the fundamental component. That is a simple definition might you get on Google also. But you might not aware about what is a fundamental component, what is a non-fundamental component, what is a fundamental frequency, what is a non-fundamental frequency. So we will understand it from this figure. So this what this second sentence tells us. In this figure, 50 hertz sine wave is a fundamental component. Okay, so this is green line. Green line is a fundamental component. Fundamental component means in India we are using a 50 hertz frequency. So we will consider it a fundamental frequency or as a fundamental component. Whereas the third harmonics and the fifth harmonics are non-fundamental frequencies. So third means 3 times of 50. 50 our fundamental, or 3 times of 50, 150. So 150 is this one. Third means blue one. So this is the our fundamental third harmonics, non-fundamental frequency, and this yellow is the fifth harmonic. So you might mm, uh, aware about what is a non-linear load. Non-linear load means a power electronics load, like a semiconductor devices, like a GTOs, like a MOSFET, like a transistors, rectifiers. Such non-linear loads create, or what non-linear load doing? What non-linear load doing? You are aware about the SCRs. What SCRs do? There is only a gate pulse. When the gate pulse is applied, this conduct and the current flows from up any direction. We can consider from this direction to this direction. Okay. So if I fire this SCR at this line, so what is the final current taken by the load? It's only this amount of current. This current, this small current, not taken by the load. So due to these firings, due to this continuous firing in the system, our sinusoidal waveform spoiled and become this type of waveform due to this non-linear device, due to rectifiers, due to transistors, due to CFL lamp, due to drives, different drives, the personal computers also, laptops also, because that is also a charging system in which we are using a power electronics device. So finally we got this type of input current when we are checked to the supply side, and it is a very malicious current, very unclear waveform. If you are seeing sinusoidal waveform, it should be like clear this, and it's spoiled. So what this spoiled waveform create, which type of disadvantage, we will see in the problem definition soon. Just understand again this figure. So this is our third harmonics, and this is our second harmonic. These two, this 3 and 5th, 3 means 150 hertz, 5th means 250 hertz. These two superimpose this fundamental frequency, green line, and it's create a final this red line resulting waveform. You can see here it is not a sinusoidal, it is spoiled. Okay, so this is our time domain graph. You can see here with respect to time. We can convert it into a frequency domain graph also for better understanding, what is a harmonics level in the system. So it is a 100%. It means a 50 hertz supply. It's a magnitude of the 50 hertz supply is a 100%, and there is also some another frequency in the supply. It's a 150 hertz as well as a 250 hertz. So 150 hertz, the component level is a 23%, and for 250 its magnitude is a 11%. So these two create a total harmonic distortion. THD means the total harmonics distortion, and by this formula you can, so by this formula 20, this 108 means the 100 percentage of fundamental, and 23 percentage from the FFT analysis. What is the FFT analysis? We will see in the MATLAB simulation. So just understand what I am speaking. So this is a 23 percentage and this one is 11%. And finally, after calculating, we got a 25.5 percentage. So in this waveform, in this resulting waveform, 25.5 percentage total harmonic distortion are there. It spoiled our green, our fundamental frequency. So for understanding these two waveform, you have to idea about this slide. So this is a time domain and this is a frequency domain. Okay. So you can see here different waveform. The red waveform is a major waveform, you can see, and this another blacks waveform, well, blacky waveform are there. So if I am separated these waveforms, the superimposed waveform, I get this type of two different waveform. And if I am seeing, if I am standing here, if I am standing here and looking the waveform, then I will see two different bar located at this side on this surface. So this is how we are analyzing the harmonics. So if you go much more detail, you can see here this is our fundamental frequency. It is a 100%, and third harmonic is 20%, fifth harmonic 60%, seventh harmonic is a 50%. And after without harmonics filter, we are getting these types of harmonics. And if you connect a harmonic filter, we can eliminate the harmonics from the system. We can reduce the harmonics from the system. There is some IEEE standards also. So voltage harmonics should be less than 5% and current harmonics should be less than 8%. We will see it later. Just I am explaining what is a harmonics, how the harmonics superimpose in the system, what is a time domain graph, what is a frequency domain graph. So this is our time domain graph, this is a frequency domain graph, and it is like this way. It will be analyzed like this way. If you are standing here and see the waveform, you will get a two different graph. This is a final waveform. If I connect these two, I will get a this waveform, and if I separate these two, I will get a this type of waveform. So here you have, in the majority of the system, 3, 5th, 7th, 9th, 11th, 13th, it's not a 9th, 11th, 13th, 17th, these types of harmonics majority present in the system. You can see odd numbers of harmonics are mainly present in the system. Even numbers harmonics are not present in the system. Why even number harmonics are not present in the system? So I am explaining you. This is our fundamental frequency, and if you want to fourth harmonics, what is the fourth harmonic? Fourth means this is a 50 hertz. So fourth means 50 into 4, 200. So for 200 hertz, it will like this way: 1 2 1 2. Okay, 1 2 1 2. In it, what happened when we are going with the fourth harmonics? In the fourth harmonics, is a positive amplitude, this is a negative amplitude. With a positive amplitude, this is a negative amplitude. So every time this positive amplitude will be conquered by the negative amplitude, these two effects will be cancel out the each other, and finally we don't get any resultant waveform. But when you are talking about the third harmonics means, if I am covered by for this one, 1 2 and 3. So positive and negative cancel out the effect of each other, but this positive remain, and that finally spoil, that finally superimpose this our main waveform and creating the error. So every time for the even number, it will cancel out the effect of each other by positive and negative. But for the odd harmonics, there is always some resultant magnitude present in the system, and that superimpose our fundamental frequency and finally spoil our fundamental frequency. I hope you understand what is a harmonics by this way. Majority basic parts, majority of understanding you got from this up to this lecture. Now we are switching to the problem definition. Why the harmonics filters are required? Now you know harmonics are present in the system. Harmonics are created in the system due to non-linear devices. So this project is based on design of passive harmonics filter. Passive harmonic filter. What is a passive harmonic filter? We will consider it as soon. To improve the power quality. To improve power quality. This is a spoiled waveform and I want to improve to this level and mitigate the harmonics adverse effect. There is the adverse effects of harmonics, there some heating, some malfunctioning of the device. We will consider it later. Just follow the steps. Nowadays, many loads are non-linear in nature due to exponentially use of the power electronics component. Most of the power electronics component are the cause of harmonics generation. Harmonics are produced when non-linear loads such as a rectifier, AC/DC drives, UPS, SMPS, arc furnace, CFL lamp, welders are connected to distribution system. Obviously, we are using this system nowadays very high amount. In industry, it is a very high amount, and if you don't connect a harmonic filter in industry, you will definitely get a majority of harmonic current in your supply system. In Maharashtra as well as some another state, the government are billing the industries by checking harmonic level also, the KWH billing. So in another states also this implementation will soon apply. So we have to connect harmonic filter if your system is creating the harmonic. Otherwise, you will have to pay a high amount of penalty to your electricity supplier. That is a final. When the harmonics are introduced to the system, the sinusoidal voltage and current get disturbed. Get disturbed. Voltage and current both get disturbed or deviated from the fundamental frequency. Yes, deviated. This is our fundamental frequency and it is deviated to this red waveform. Due to the load may get damaged, the harmonics effect. It is created due to this harmonics current, this unnecessary harmonics current created in the system. Harmonics lead to a copper loss, iron loss, dielectric loss, thermal stress in the cable, transformer, rotating machine. What's happened in the rotating machine? If the fifth harmonics is in the system, it will oppose your rotation of your motor. If the majority of harmonics are fifth harmonic, it will affect it will create a back pressure, it will create back EMF in your winding to oppose the rotation of your electric motor. That's why fifth harmonics you have to dominate, you have to clear the fifth harmonics in the system if there is a harmonics. Okay. The nuisance stripping, malicious stripping, unnecessary trimming are also one major reason of the harmonics. Also, a driver failure of your LED lights. Sometimes the driver that is used to drive your LED light might be fail after some time period, like every 2 months, every 4 months, you are facing the issue that your LED lights drivers are failing continuously. That is also due to harmonics. And in industry, you might notice that your LED light filter damage or even you connect a proper LED light drivers, you might notice that it will fail after 2 to 3 months. Even its lifespan is more than it. And it is all happen to these harmonics and the different spikes that are continuously in our system. So I think so I have covered most of things about the harmonics very clearly. So we are now going to in depth what is our project. I think so this video will become a very long, but if you see all the steps perfectly, you will get a more idea about it. So types of harmonics filter are passive harmonics filter, active harmonics filter, and the hybrid harmonics. Hybrid means it's a combination of active and passive. What is a passive harmonics filter? The simple L and C combination. This is the L and C. L, C, R combination create a different harmonics. We will consider it soon, and we will see the different these graphs. This same graph in MATLAB also. The same response in the MATLAB by calculating these values, by arranging this value in the MATLAB simulation software. So what is a passive harmonic filter? In this project, we will analyze and design. We will analyze as well as design. We are designing the passive harmonic filter in MATLAB Simulink software. Passive filter are the best suitable for a constant load, where the load is constant, that is not vary. Like if some industry there is a constant load, if even industry most of time constant load is going on, and if you are checking the harmonic, if you are studying the harmonic study is a major topic in which some vendor come to your industry and check the level of harmonics by putting some instrument like a fluke. Fluke is a fluke harmonic analyzer. Fluke is a company that is creating the different instrument, different checking measuring instrument. You can see, you can connect with any vendor that is doing the harmonic study. They come to your industry and with that harmonic analyzer and put it into your system and check for 1 to 2 days what is your level of harmonics and which level of harmonic that are continuously changing in your system, and that spoil your system. And in a constant load industry, majority of harmonics are third, fifth and seventh harmonics. Might be a 13 or 70s are also there. So these harmonics are majority of harmonics that is in your system, that is in your industries. Passive harmonics filter are combination of resistance, capacitor and inductor in different series, as well as parallel combination or mix up. So series, parallel or mix up. Okay. Passive filter is tuned at a particular frequency. What is a tune? What is a tune? For tuning, you have to understand what is a resonance. We are tuning, it is a resonance frequency. So what happened? What if you go to my dynamic wireless charging system video, that is also one of the unique project. So if you go to that video, in that project I have most ofly covered what is resonance frequency. So I am just briefing it once again. So in RLC series circuit, uh, if you are designing or if you are supply this series circuit to a resonance frequency supply, it means if I calculate how to calculate a resonance frequency for series resonance frequency, there is a formula fr is equal to 1 upon 2 pi under root L into C. So what is L? This is the L and this is the C. This is the R. So resonance frequency, if I am supplying this circuit to at resonance frequency, what will happen? The XL, the effect of XL, uh, inductive reactance will be cancelled out. The effect of XL will be cancelled out by the XC. XC will help to cancel out the effect of XL, and there is a final impedance is remaining in the system is only a resistance, so what happened while I am selecting this filter, like if I want to reduce the fifth harmonics from the system, I want to remove the fifth harmonic. So this is my load and that is creating the fifth harmonics only. And if I connect the filter by RLC filter, or you can see it is a single tune filter, R, L and C. Okay, R, L and C. In if I am tuned this filter by this formula, fifth harmonics means I want to reduce the fifth harmonics. Fifth harmonics means 5 into 50. 5 into 50 means 250 hertz. I want to reduce, or I want to set, or I have to set this filter. I have to tune this filter as a 250 hertz. So if I tune, so if I write a 250 hertz here and calculate different formula L and C unknown, you can consider L as a any value. If I am consider, let's consider C is a 2 microfarad. By considering the 2 microfarad, I have to find the L and I have to put my resonance frequency at a 250. By this I can calculate the L and C. Okay, so if I tune this filter at a 250 Hz, so all the fifth harmonics will be fifth harmonics current will be go to this part, and our fundamental current go to this part. So I can improve. So if I grounded it, actually in system it's like this way, it's my load, and it's my harmonic filter. You can see this one. Okay, so uh, all the harmonic current that is diverted to ground by this way. Okay, so this is how you have to set. So here I explain this thing. So if you want to eliminate fifth harmonics from the system, yeah, like this way, like this way, this is a filter. Okay, this is a harmonic generated load. So all the non-linear current, harmonic current will be bypassed to this way. Motor is not creating the harmonic. The power electronics device mostly creating the harmonics. If you want to eliminate the fifth harmonics from the system fundamental frequency is 50 Hz, then tuning frequency is a 250 Hz. That's why I have used a 250 Hz. 250 Hz. My resonance frequency is a 250 Hz. Just consider, you can consider any value. If you want to consider L, then you can consider L, any value of L, and then calculate C. If you consider C, then select any value of C, any random value, and then calculate a L. So by that two value you have to uh, set here, or you have to attach here, and simple resistance R. Okay. So in your resonance, if you are checking the frequency versus impedance graph, I am a frequency at a particular frequency you get a very low impedance like a U type, and that is only a resistance, because C and L cancel out, XC and XL will be cancel out the effect of each other at a particular frequency, and only resistance is present in the system. So this resistance is only this value. So you will get a minimum impedance, and as your minimum impedance, most current flow that path, because current always flow the minimum impedance path. So this is a very simple logic, but very good, or very interesting you to understand this topic. So according to this resonance frequency, you have to design the resistance, capacitor, and inductor for all the filters. So these four filters we will design in this video: single tune filter, double tune filter, high pass filter, C type filter. This is an impedance graph, impedance versus frequency graph. It's a simple. This is for two times. So if you want to remove the fifth harmonics as well as the seventh harmonics, both harmonics you can remove by this single filter. If you want to remove the fifth harmonic, you have to, or if you remove the fifth and seventh both harmonics by this single tune filter, you have required two different filter. One is for fifth harmonics and one another is for seventh harmonic. But if you want to use only one filter and to remove two different harmonics, you can use double tune filter. Okay, for reducing the very low order of harmonics, uh, for very low order of harmonics, like a third order harmonics or fifth order harmonic, particular that harmonic, low order harmonic, we will use a C type of filter. And for high order harmonic, so if you want to reduce more major of the harmonics, if you want to reduce a major of the harmonics like a fifth harmonic, seventh harmonic, 11th harmonics, we can use a high pass filter. High pass is the most probably high order harmonics will be removed from the system. This is a basic understanding of these four filters: single tune, double tune, C type, high pass. Single tune is for the particular one harmonics. Double tune is filter two different harmonics at the same time. C type of filter is used to low order harmonics, particular third and fifth. And for majority of harmonic, that is higher order harmonic, if you want to reduce higher order harmonic, you can understand by this graph also. Every graph is going upward very sharply, but it is not going upward very slightly. It will follow this path, bending path. Here also we can reduce majority of harmonic. You can see the response. We will see this response in MATLAB also, so don't worry. This is a simple understanding. So now we are on. So now we are on our MATLAB simulation. So you can see here, uh, This is our MATLAB simulation file. The file name that I will share is main.slx. This is the name of file in which you get this file. This file means there is a simple non-linear load or power electronics load that is connected to your supply system. So what you have to analyze here? In next slide you have to do FFT analysis. How to do FFT analysis? I will make a separate video on it. How to do the FFT analysis in MATLAB simulation and how to open the FFT analysis in MATLAB simulation. So after the FFT analysis, you can see we got a voltage harmonics is 0.63% for this circuit. For this circuit, voltage harmonics is 0.63%. That is under limit. According to IEEE, voltage harmonics should be less than. And for current harmonics, next slide. For current harmonics, when you do the FFT analysis for current harmonics, you get a 29.98%, that is nearly 30%. That is a more than recommended limit. It is a more than 8%. That's why the system failed. And here what we have check for current, what we have taking the parameter. This is for current. Okay, current harmonics. This is a I and this is a V for voltage harmonics. How to open this I will explain in MATLAB simulation also. This is a 10 number. I have considered a 10 number cycle. First 10 number cycle. So most of things cover in this 10 number cycle because all the cycles remaining are same. And we are taking our fundamental frequency is a 50 Hz because in India the fundamental frequency is a 50 Hz 230 volt. Okay, and this is a harmonic order. So you can see here this is a harmonic order graph. You can see the fifth harmonic. So fifth harmonic is a nearly 22%. Seventh harmonic is nearly 11%. Ninth harmonic, 11th harmonic is nearly 9%, and 13 harmonics is a nearly 6%. You can see here we are getting this type of harmonics 12, 2%, 11%, 9 and 6%. Now you have to mitigate, you have to remove these harmonics from your system. So this is a current time. When you measure a current here, this is a current measurement, this is a voltage measurement. And if you measure a current, you get this type of improper waveform or inaccurate waveform. You want to see this, we can go with the MATLAB also. Yes, this is a MATLAB file. You can see here when I simulated is main load dot main load dash. So you can see here we are on our MATLAB screen and I opened the main dash load SLX file that I have already mentioned the name of the file, main dash load dot SLX file. I have opened it and you can see when I run it and the run is completed. You can see the different voltage waveform here, current waveform here, and this is the final output. Yeah, we are and this is the RL load and this is a line loss. Due to line loss there is some losses occur, so that's also I have considered. So you can see here the voltage waveform. Voltage waveform is very accurate. I don't think so. Okay, yes, sorry, yes. So voltage waveform is very accurate, and but there is some notches and this notches created some harmonics. That's why we got a 0.63% only harmonics in the voltage waveform. It's a very less 0.63% due to these notches, but it is a tolerable. But when okay, when you check the voltage current waveform, not a voltage, it's a current waveform, you can see here very inaccurate waveform we are getting, and due to this inaccuracy we get a harmonics in our current. So now you want to mitigate the harmonics, so you have to connect different filter in here and we have to mitigate harmonics. So this is the output, a current. We are not much more interested in the output. There is some variation because I don't use any filter capacitor here. For getting accurate result of the harmonic filter, I simply use a load, and load means RL load, and the three phase rectifier, and this one is our voltage measurement, and this is for current measurement display. So this is a simple main load. So now again, how to do FFT analysis, how to find FFT analysis, I will make a separate video and give the link in the description box. How to open this slide, how to open this FFT analysis. Actually you have to go to power guide and then tools and do the FFT analysis, but there is some changes you have to do. that will cover in the next video or a separate video. Just focusing on the output. So here the current harmonics already we have covered. This is the harmonics that we are facing here. Now we have already seen this video scope. This is a this one scope. Yes, this one we have already seen in this file. Yes, this one. Okay, so it's an inaccurate waveform that we are getting. So I want to improve, I want to reduce these harmonics from the system. So what I will do, first I will connect a single tune harmonic filter, because what we are doing in the previous slide, okay, this one, we are doing this, checking the response or checking the, how these all the filters work. So first we are going with this filter, then we are going to this filter, then this, and then this. Okay, so this one is in which I have used all the filter, fifth harmonic filter, seventh harmonic, 11th harmonic, 13th harmonic, and I have used a simple component. This is a directly available component in the MATLAB circuit. So if, in which what you have to do, you have to just set the tuning frequency. For fifth harmonic it's a fifth into 50. For seventh harmonic is a 7 into 50. 11th harmonic is 11 into 50, and 13th harmonic is a 13 into 50. So these all the four filter mitigate the particular harmonics. These harmonics mitigate the fifth harmonics. This fifth harmonics filter mitigate the particular fifth harmonics. Seventh harmonics filter to mitigate the particular seventh harmonics. 11th harmonics filter mitigate the particular 11th harmonics, and 13th harmonics filter mitigate the particular 13th harmonics. So in previous slide you can see this all the harmonics mitigate by this individual harmonics. Okay, so you can see here you have to set a 5th, 7, 11, 13 according to 5 into 50, 250, 7 into 50, 350, 11 into 50, 550, 13 into 50, 650 respectively. Okay, so if you do FFT analysis file, this the name of this file is basic one single tune harmonics filter. So if you open, I will share what I will share. I will share. Okay, in project you will get this all the SLX file. This is a main loaded SLX file, and this is a basic one single tune filter that we are actually watching at now, this one. So again now we are opening this file, and the name of this file basic one single tune. Okay, so name of this file is basic one single tune. So you can see here uh, uh, this is a file. When I simulated it, it finally got simulated, and after connecting this filter we can eliminate the particular harmonics. If you want to eliminate fifth harmonic, seventh harmonics, 11th harmonic, 13th harmonic, for the all the harmonics order I have used a separate harmonic filter. So after the simulation, what you get here, you can reduce the voltage harmonics to 0.63% to 22%, and current harmonics to 29.98%. That is in this, in major load without any filter. In this main load we are getting these two harmonics level. For voltage harmonics is a 0.63%, and the current harmonics 29.98%. So this is our main load, and there is no any filter connected here. Now if I connect the filter, this is a direct filter that is directly available in the MATLAB. There is a component, a fixed component. Just I have to set to a single tune filter. So I have used directly it by setting the frequency of it, like for fifth harmonic is a 5 into 50, for seventh harmonic is a 7 into 50, for 11th harmonic is 11 into 50, and for 13 is a 13 into 50. It's a very simple. You have to directly set the frequency for tuning it. So so if I am open it, if I open this circuit, so this one, and there is some impedance measurement also. So for checking the impedance measurement, what is the impedance measurement at particular frequency, what is the impedance provided by this circuit for this load. So for impedance measurement, and for linear impedance and linear frequency, and I want to check it to 10 hertz to 1000. Okay, when I update it, you can see here, you can see very clearly at a 250 hertz, we are getting a minimum impedance, as well as at seventh harmonics. For fifth harmonics is a 250 hertz. So at 250 hertz we are getting a very low impedance. At seventh means 350 hertz. At 350 hertz also we are getting very low impedance. At the 11th is 550 hertz also, and 650 hertz also we are getting very low impedance path. So it is follow the same. So what happens, this low impedance path means all the 250 hertz current, all the 250 hertz, sorry, all the 250 hertz current will be passed through this way and ground it. So grounded it. All the 350 hertz current passed through this way on grounded it. All the 11th means 550 hertz current passed through this and grounded. And we can, by this we can eliminate the harmonics. You can see here, we have eliminated the harmonics 2.22 percentage by these filters, and 0.38 percentage for current harmonic. How to open this FFT analysis will share by different video. So again this is a advanced model. Advanced model, it means in this model you have used the internal component of the MATLAB, but when you are actually designing the system you have to calculate the RLC value according to hand calculation. You will get this calculation in mathematical PDF that I have already shown you. You will get this file mathematical modeling. You will get all the calculation of this value. This advanced means actual model. Why I have used this name? Advanced means actual model in which you have to calculate all the things. So I am opening this circuit, okay, in the MATLAB. So if I go into MATLAB and go to open, and I want to advance single tune harmonic, if I open it, you can see here the different RLC component that I have calculated and I have used. Okay, yes, RLC component I have used. So first I am simulating it, and for this one, what is the level of harmonic you have mitigated? Okay, actually you have mitigated a voltage harmonic 0.63% to 0.54%. It is already in limit, and the current harmonic you have mitigated from 30% to 0.56%. You can accurately remove the current harmonics also. Now you are again measuring the impedance. So you can see here same as above. At 250 hertz also you are getting minimum impedance. At 350 hertz also. At 550, at 7 at 650. Okay, according to this harmonics level, according to these filters, you have used these filters. That's why you are getting this response. If I remove this 7th, 11th. So in this file I am actually removing this filter. Okay, first check the impedance without removing any filter. So after a particular simulation, what will you get? It takes some time to simulate. After a simulate, if you check the impedance, you can see here you have to find a linear and linear frequency, and the range of this is 10 to 1000. Okay, update. Okay, so you can see here accurately we are getting a 250, 350, 550, 650. We are getting a minimum impedance at particular this frequency. But if I remove these filters, so at this point you have to get a minimum impedance only at 250 hertz. So again I am simulated it and checking is it okay or not. Okay, so finally it's a concluded. And again if I opening the impedance measurement and update it, it takes some time to update. Yes, you can see here we are getting exactly at 250. Why this happened? Because we have removed this filter 7th, 11th and 13th. Only 5th harmonics filter is there, and that's why only 250 hertz frequency we are getting a minimum impedance. So this is how accurately we can design the filter. Okay, so I am no okay. So we are going further. Okay, so this is the, now we have done with the single tune filter. In previous slide you can yes, in what we have done this filter, and we check a response also. At a particular frequency we get a minimum impedance. You can see in this graph, by this graph, at a particular frequency we get a minimum impedance. It's the same. Now we are checking the double tune filter. So what actually happening with the double tune filter? Double tune filter give a two different frequencies, give a minimum impedance at a two different frequencies. So now design the double tune filter. So also there is a two ways to design a double tune filter. One is a simple way in which you are directly using an internal component of the MATLAB, and another is you are calculating the all the LC combination and checking the double tune filter. So let's get started this filter. So now we are switched to the double tune filter. This is our second filter and you want to analyze this filter. So by this one filter, by this one you can eliminate fifth as well as seventh harmonics both. And by this filter you can eliminate 11th and the 13th harmonics both. So in previous filter, for eliminate the different harmonics you have to use a separate filter, but by this filter, double tune filter, why it name is a double? Double means two frequency or two harmonics can be mitigated at a particular one time. So you can check this in the MATLAB also. If I open this file, yes, this one, you can see the 5 and 7 filter, 11 and the 13 filter. Just simulate it, and you will get, you can eliminate the harmonics. So how to open the FFT analysis? FFT analysis takes some time to open, but we are directly going with this FFT analysis that I have already done. So by these two filter, we can eliminate the voltage harmonics, that is a 0.63% and 2.19% is very accurate, and the current harmonics 30% is to 0.63%. So also very good. We can eliminate the harmonics as current harmonics as much as possible. So now we are going with the actual model, advanced dot double tune filter. So again we are going with the MATLAB advanced dash to double tune. Okay, this one. So it takes some time to open. Yes. So in this one I have calculated different value L and C, and when by this way, by this filter we can eliminate the voltage harmonics to 0.14% and current harmonics to 2.65%. Yes, it is a slightly more, but it is under the limit. It is a less than 8%, means it's under a IEEE limit. So by this calculation, by this calculator values are L and C, actual model value, we can eliminate current harmonics as well as voltage harmonics also. Now again you want to check a impedance graph. So I am opening that, yes, and simulated it. Now you want to check this one. This is the impedance graph of the RLC, double tune RLC combination. So it's a double tune, yes, this one. So for checking the impedance, I'm double clicking tools, impedance measurement. So you can see here, when I press upgrade, yes, you can see here at a particular frequency like a 250 hertz. By this only one filter we get a two different minimum impedance at 250 hertz also, at the 350 hertz also, for fifth harmonics also, for seventh harmonic also. And for this filter we are getting for 550 hertz also and for 650 hertz also. So it means one filter can do or can remove two different harmonics from the system. Okay, so same I have explained in this slide. I think so you understood this double tune filter also. Now we are going with the high pass filter. So now this one is our high pass filter, in which most probably higher order harmonics can be removed by this high pass filter. It's an internal component. That's why the name of the file is starting with the basic. When there is an internal component of MATLAB, I have used a basic, and then when you are designing the actual system, you will get an advanced here. The name starts with the advanced. Advanced means you are designing the actual system, and basic means you are directly use the internal component of the MATLAB circuitry. So by this filter, you can see here by the FFT analysis. Okay, there is some slightly increment in the voltage because harmonics is reduced and its adverse effect on the voltage also. We can reduce the harmonics to the 32 to 2.65% and voltage to nearly 1%, because both voltage harmonics also in the IEEE range, it is less than 5. So this is the internal component. That's why some adverse effect. But when you are actually designing the system, it's an advanced high pass tune filter. When you are actually designing the system, then you can see here voltage harmonics reduced to 0.63% to 0.58%, and current harmonics reduced to 9.96%. We cannot eliminate the harmonics. What I have done in the high pass filter is a high pass filter, and it is a particular tune for the fifth harmonics, and more than fifth harmonics, all the harmonics slightly reduce above the fifth harmonics. Above the fifth means you can see here all the harmonics. Fifth harmonics reduced from 22 percentage to 7 percentage. Seventh harmonics reduced 11 percentage to 5 percentage. So slightly reduced. All the harmonics are slightly reduced. But actually, when you are actually designing the system, high pass filter is not only used separately. You have to use any another filter with high pass filter. So what you are actually designing when you are actually designing the system, uh, you are designing the two different filter at a particular time. High pass filter is a single tune filter. In this single tune filter, it's a fifth harmonic filter. So all the fifth harmonics mitigate by this filter, and remaining harmonics mitigate by this high pass filter. So we can get accurate result. You can see here, by combining these two, we can get a harmonics 5% nearly. It's under the range current harmonic. So if I am opening the this one high pass filter internal, okay. So internal circuit is this one high pass filter, and you can see here when I simulated it, I got a particular output for this filter. When you are doing the advanced model, and you can see here the impedance graph also. You can see here impedance graph also. You want to check impedance graph for advanced model, impedance measurement update. Okay, you can see most at a 250 Hz, because we have designed a filter at a 250 Hz. We get a minimum impedance at a 250 Hz, and then impedance is less compared to. That's why we are getting mostly higher order harmonics reduced. You can see here from this graph also, we are majorly reduce all the harmonics. You can see all the harmonics are slightly reduced by this filter. So this is how you can design high pass filter also. Actually high pass filter, and we have already seen, you can see graph, impedance graph. Yes, this one slightly less. Okay, this is how you can design a high pass filter. Actually high pass filter you don't use separately, use with any of filter, any of single tune filter, any of double tune filter. Don't use separate high pass filter, because it's not as accurate as we want. So we are actually using a combination of it. This combination file also you get in MATLAB. Yes, combination of the single tune filter with a high pass filter. Yes, you can see here this file, all this all file you will get in the description box, so don't worry. Yes, it's a combination. Okay, so now we are going to further same. Yes, we can reduce the high pass combination of this single tune filter with a high pass filter. Okay, actually I have to use this name. Okay, single tune filter with a high pass filter. So now we are on the final our C-type filter. We have seen all the filter, This we have seen the response of all single tune filter, double tune filter, high pass filter, C-type filter. So now remaining is a C-type filter, and we are checking the C-type filter. C-type filter is mostly used for the lower order harmonics, particular third harmonics and the fifth harmonic. So I have designed here a C-type filter for a particular fifth harmonics, because fifth harmonics is the majority of harmonics in our system. So without any filter, our current harmonic is a 0.38%. Without any filter, our current harmonic is 29.98%, and with filter we get a 0.38%. This one is the first one. First one we have already seen. This one, basic. Yes, this one. By these harmonics we got this result. Then we have calculated a particular RLC combination and got a proper value. So by this way we get a harmonics into 0.54%, 0.56%. This is also Indian. Then we have designed a double tune filter by the internal component. So again the double tune filter, yes, this one. Directly use the internal component. Basic means directly use the internal component of MATLAB. So we get a 0.19 in voltage and 0.63 in the current. It is also in range. Then we are designing the by the RLC component. Then we design. Yes, this one is a design by RLC, particular design the system. So by designing the system, we get a voltage harmonics also very less, and the current harmony is also less or IEEE level. Then we have designed high pass filter. Again, we design the high pass filter. Okay, this one in which use directly high pass filter directly use a MATLAB internal component. Then we calculated all the value and design the high pass filter. And again for C type filter, again for C type filter we have used internal component and use RLC combination, calculate RLC value for the C type filter. And you can see here the final output, all the outputs here. And you can see here the high pass filter and the C type filter cannot use separately or cannot mitigate the current harmonic accurately. That's why we have to use some combination, a double tune harmonic filter with C type of filter, and we have used one another combination, that is high pass filter with a single tune filter. Okay, so this is how you can accurately design the system, and we are getting as similar as response as this response. So all the things that we have calculated is as accurate and as crystal clear. So now this is a mathematical modeling. It is for the main load. Main load means for this one circuit. This circuit, there is a no filter. This is a circuit. And for calculating this all the value, there is some consideration that I have covered in this mathematical modeling. This is a simple slide. All the mathematical PDF you will get in the description box, in which you will get all the value, how to calculate this capacity, how to calculate this resistor, all the formula you will get for all the filter, not this one, for all the filter you will get in this PDF. It's a 30, I think so, nearly 30-page PDF. You will get all the data. So in consideration, I was considered a power factor was a 0.65%. I want to improve to it's a 0.99%. For that, what is the power consumption actual load by RL load? What is the reactive power required to improve the power factor? Then this is a simple formula for single tune fifth harmonics filter. This one, single tune fifth harmonics filter for this one, but it is an internal component. So for this one, if you how you can calculate the RLC combination, there is some formula, and the formula is this one, y c fifth, L fifth and R fifth. This is a formula by which you can calculate the different value. For accurate result for all the things you will get in the our PDF, so don't worry, this is for your reference. Just follow the PDF, the mathematical model, handwritten PDF. You will cover all the, you will understand all the things properly. So final, what is the advantages of the system? Why we are doing this? Why we are do this all? Or why we are connect the harmonics in the system? So what is the advantage of passive harmonic filter? Easy design. You can see very easy design, very crystal clear design. Less expensive the active harmonic filter, because active harmonic filter require power electronics components and it is costlier than the passive harmonic filter. When there is a fifth harmonic used to eliminate major harmonic, you know the harmonics are fifth, seventh and 11th, 13th and 17th is majority in the system. If you know that fifth harmonics is the majority in my system and my load is a constant, then you can use a passive harmonic filter. Not mostly used for small scale industry where active harmonic filter is a costlier and passive harmonic based option. Okay, because AHF means active harmonic filter. Active harmonic filter contain a power electronics device. That's why it's a costlier. And this is a simple RLC combination, passive harmonic filter. No extra power required. There is no any power required. By connecting, we get a so by connecting this filter, we can we can get a voltage harmonics to less than 5% and current harmonics less than 8%. And there is a no limitation on the frequency range. You can design this filter for any frequency you want, so don't worry about it. This is the final conclusion. By going through this elaboration, we can design a passive harmonic filter especially for majority of harmonics. For any frequency we can design the filter. There is a no restriction on it. For any frequency you want to design is a 13 hertz, 13, you want to design the 14, you want to design is a 11. Not because these harmonics are not majorly, second harmonics are not majorly affect the system, because what happened in the second order harmonic. Let's consider the fourth order harmonic. So you can see here positive, negative, positive, negative. So positive and negative cancel out the effect of each other, and there is no any final superimposed in on this line. But when you are designing the third harmonics 1, 2 and 3, So you can see here plus minus will be cancel out the effect of each other. Positive negative cancel out the effect of each other. But this positive remain in the system, and that finally superimpose this our waveform and spoil the power quality. The design of this filter depends on the system demands such as the harmonic order to be eliminated and the reactive power to be compensated. Also the parameter depend on the system such as bus voltage, system frequency, will factor, resonance filters. Yes, which all the depend on the system voltage and parameter. And by passive harmonic filter we can accurately remove all the harmonics from the system. So these are some reference. You will get this reference paper also in the description box. Thanks for watching this video. If you have still any query, just comment it. I will definitely reply. If you have any query, we can meet on Google Meet also for any query. And if there is some another video and for FFT analysis, FFT means fast Fourier analysis, I have made a separate video and give to link in the description box for checking that how you can get this slide, how you can open this FFT analysis. There is some procedure you have to do in the MATLAB to open this procedure analysis. So that's why I have used a separate video. I will make a separate video on it. So you will get all the things clear, all the thing will be clear to you. So again, thanks for watching this video, and if you have still any query, just comment it. I will definitely reply. Thanks.